So, good morning. Welcome to Krishna's classroom. We continue from what we did last time. We spoke about the concept of outer measure, but let us make things very precise and rigorous now. Okay. So, you know that I'll just recall a few facts, namely, measure is a non-negative real valued function defined on a collection of sets, and what we are after is to define such a function with a certain properties which we have already identified on subsets of R, and this of course involves one particular requirement, namely that if AI belongs to the class of subsets PR is the power set of R, then and AI intersection AJ is empty for I not equal to J, suppose I one to infinity, etc. Then we would like to have this function, that is, which let us denote by m of AI so m is the function from R star. R star is R union the points at infinity. Yeah. And of course we have m of AI is and now this requirement, so we are trying to define a non-negative function on a class of subsets, if possible on the entire class of, on the whole of PR, which we don't know whether it is going to be possible, such that it is non-negative, it is additive in the, or countably additive in the sense that m of union AI equal to sigma m AI whenever AI intersection AJ is empty for I not equal to J. And of course you have it is defined on the whole set R and also for empty set and so on. Therefore, the collection A, now this suggests a certain structure on the classic. What is it? That A is a subcollection of the power set of, that is the first requirement. 2, the whole of R belongs to, then the empty set belongs to, third property is that A belongs to A implies A complement belongs to. Then you have the fourth property, namely that AI belonging to A implies union AI belongs to this is the countable union of the collection here. Okay. So, of course, here we are not putting the restriction that AI restriction AJ is empty. It may be empty or may not be empty. So that does not matter. There may be overlapping, but still you should have this. Now, if all these properties are satisfied by this collection of sets, subsets of R, then you say A is or A sigma algebra of subsets of R. Now you have the concept of measure. What is the concept of what does the concept of measure say? See that one of the properties that is required is that M of and plus infinity that means M is a map from A into, let me put this so that infinity is also included in this. So M may take infinite value plus infinity also on some subsets of. Then you should have the following property, namely that if AI intersection AJ is empty for I not equal to J, then Now this is a crucial property. Okay, and we should have necessarily m phi equal to 0. So we are actually on the lookout for a function of this kind. Now in this, our task is possibly to have this collection of subsets of R as large as possible. Okay, and we would be extremely happy if we could do it, define such a function on the entire set of subsets, because you know that PR satisfies all these properties. Okay, right. But the difficulty is that, you know, it's not quite easy to satisfy this condition. To choose at the outset, to choose a function on A satisfying this property, satisfying this particular requirement. And that is why we take an intermediate step and we relax this condition in the following. We relax this condition by the following requirement. That is, here we will be talking about a function. Say I want to designate it by m star. Less than or equal to that brings some kind of ease to define such functions. Instead of m, you define some function m star, where all these requirements are true. That is, we should have this m star is mapped on A to infinity. Then m star is also zero, and possibly with this relaxation, that is replacing the equality by an inequality, we are in a position to define m star on the entire power set of. Okay, so our strategy is this: we will define a set function on every subset of R, okay, which has the property that it's a map from PR to 0 infinity. M star of the empty set is 0, and then instead of additivity, that is what is required in the definition of measure, we get the condition replaced by what is called subadditivity. Namely, the equality that comes there is now replaced by inequality. Okay, so this is what we do. And such a function is what you call an outer measure. Okay, so this is the crucial point. Instead of such an stringent restriction, we replace it by a sort of more easily manageable requirement, namely what is called condition of subadditive. Okay, that's the whole idea. So that gives you what is called, and that makes it possible to define on the entire PR, because we don't know, because of this restriction we do not know whether it is possible to make this satisfy on all subsets of PR. Okay? But certainly this is possible. So let us start with this. And what more requirement is that we are asking for? In fact, the function that we define in this way should have two other possible properties, namely that it should be we would like M to be translation invariant, namely M of this is called translation invariant. The other property is that I every interval measure of an interval should be equal to the length of the interval. This is what eventually helps us to connect the Riemann integration with Lebesgue integration. Okay. So these are two other conditions that this function M should satisfy. Okay. And as such, we first demand that M star satisfy all this. So M star is now defined that means on some sets it may take the value infinity also, so that M star of here to M star of an interval is equal to the length of the interval. The third criteria is that M star is translation invariant, that is The fourth property is that M star of union AI. So our task is now cut out. After this, after doing this, we will think about how we can define M, because how you can strengthen this particular relation and replacing it by an equality, and if necessary, by throwing out some functions from some subsets of R from this class. Okay, where you can comfortably define such a function. So that we will explore at the next stage. This M star is called a noun. How do you possibly define this? This is the problem. Because we are saying that we are going to define a function of this kind for all subsets of the real life. So let us see how we introduce this. Now before that, we make certain definitions. How do we do this? This is our next task. So for that, let I denote a non-empty interval. It may be an open interval or a closed interval of real numbers. Then I can take different forms, AB or equal to AB equal to or equal to doesn't mean that this is equal to this, or write this way. I equal to open interval AB or the unbounded intervals. These are all bounded intervals. So we take A infinity or I equal to minus infinity A or I equal to, these are all unbounded intervals. These are all bounded intervals. We take minus infinity less than A, than B. Okay. Now we define the length of I. Li, the length of I, is infinity if I is unbounded like the three cases that appear here, or and is the difference of or what you call non-negative. Of the endpoints. That is B minus A. So that's the definition of the length. So this is all we are all very familiar with. Now let us see how we define a function of this kind. The art of doing it is to cover the given subset as the or enclose it inside a countable union of open intervals. So given A contained in R, that is a subset of R, consider the countable collection of open intervals, non-empty, intervals, non-empty, open, bounded intervals such that A is contained in union K equal to 1 to infinity Now this is not difficult to see. So if you choose any subset of R, take all the rational points in that set. Okay, and then for some epsilon positive, you list those rational numbers, and then you so this is what we do. Consider the set of all rationals enumerated as x2, or let me write R. Now consider open intervals where epsilon is positive. Then A is certainly contained in now this is because that is the set of rationals, that is Q is dense. Therefore, A has always a can always be put inside a countable collection of open intervals. Okay, right? Therefore, we have seen this packing. Now we will define M star as positive. Let provide A with a open curve. Then sigma k equal to 1 to infinity, length of ik is uniquely now you see this may be finite or infinite. But it is uniquely determined. Okay, this is because, and this is the reason we also make this statement, because L of ik is positive, it's not negative, and therefore the above sum is independent of the order of the summation. That is now we are in a position to define M star. So we define the outer measure of A denoted by M star A as follows. M star of A is defined as infimum of sum of Lik, where Ik, the collection Ik provides a open cover for A. A is contained in so summation taken over all these possible covers that you can, so the infimum taken over all these possible covers that you can take. The infimum exists. Because the above sum bounded below by therefore the infimum exists. So there is no problem about the infimum. Now, what are the properties of? So this gives the definition of M star. So what have we done? We have packed A into the union of collection of open intervals, and then take the sum of the lengths of these open intervals. Now do this for every possible packing of A. Take the infimum of all these numbers that you get. For various packing, it is going to be various numbers, but all these numbers are going to be bounded below by 0, therefore the infimum exists. Okay, and that infimum is defined as what is called M star. Right. So let us look at the properties of this function. Now we have a set of properties that we ask for this function m star, whether it meets all of them. Now this is what we have to explore. Okay, so let us explore. Now the first thing that we observe is that equal to 0. Okay, because the empty set is a subset of every set. Therefore, it's quite easy to pack it inside a interval, an open interval of length as small as we please. For every epsilon, it is possible that entire force exists. That is true. The second property is that if A is contained in B, then m star of that is a monotone property for m star. Okay, that's quite easy to say. A contained in B we are talking about any subset of R, not necessarily an interval. Is an open cover for it. Hence, now what we prove next is that third property, every countable is m star of A equal to 0. So we prove this. Prove this. One to infinity. For epsilon positive, shall be given arbitrarily, and for each natural number k, ik defined by the open interval is a collection of open intervals such that C is contained in Ik. Now m star of C by definition is infimum of okay, and this what is the length of Ik equal to epsilon divided by 2 to the power. Therefore, sigma this is equal to epsilon, which implies any epsilon positive. So you can choose epsilon, any epsilon positive. Now that is of course 0. Therefore, every countable subset of R has outer measure 0. Now what we see, these are the properties that the empty set should have its outer measure 0. If A is contained in, then m star of A is less than or equal to m star of B. The third property, desirable property, is that the countable subset has outer measure 0. That is also satisfied by the definition that we have, the way in which we have defined the outer measure. Now, let us show that the outer measure actually for an interval is its length. So that's a very important result. So here So we state it as a theorem. It is now we have already defined what length of I is, and we defined what is M star of any set. Okay. Now we show that if the set happens to be the interval, then this is equal to the length of. So let us prove this because this is very important. This actually shows that this is the result that is required to connect it up, the so-called Lebesgue integration with the Riemann integral. Okay. As we shall see later, I will make a comment about it later. So we prove this as follows. First of all, the first part is let I be a closed bounded interval. That means I is of the form AB, where minus infinity or even this is possible. Okay. Let us now work on this. Now you observe that AB is contained in that is an open interval A minus epsilon to E plus epsilon for every epsilon positive. This is true for every epsilon positive. It is simply this. This is the interval. This is A minus epsilon to E plus. So it is contained in it for any epsilon. Now therefore, from the definition of M star, M star of interval AB is less than or equal to B minus A plus 2 epsilon. So since epsilon positive RP2, it follows that now this is one part of quality that would, in fact, we want to get this equal to B minus A. Therefore, what is required? I mean, straightforward. I mean, you have to show that this is less than or equal to B minus A. So we claim that so this is what we have to prove now, the other side of the inequality. So what we want to prove is this. Okay. So this is equivalent to showing that. So we show that if is any countable open intervals such that AB is contained in union, okay, then what we have is that sigma k equal to one to infinity length of is greater than or equal to B minus. That's perhaps quite easy to see if you understand what exactly we are talking about. Nevertheless, let us give a proof, because we also should learn how to write the proof. Now, you see that this is an open cover. See, AB is closed and bounded. Union is an open cover for therefore by Hine-Borel theorem, this is the compactness that you are using. There exists a finite subcollection k equal to 1 to n, covering see, you should not mistake this. This does not mean that the first n ik's provide a cover for a. What it says is that from among this you can choose, say, a finitely many intervals ik such that their union will give a cover for this, and we rename. In fact, if necessary, we just rename or those open intervals. So that is to be borne in mind. Here, of course, what we are using is the compactness of the topological. So there is for every open cover, there is a finite subcover. We are using that result. Now what we show is that for such a cover, this is what you have. You have sigma k equal to 1 to n okay, right? Now, because of this property, that this provides a cover for I, you see that A belongs to implies there exists one ik, at least one, such that okay, let this be designated by A1 B1. So what is the outcome that you have? Now suppose B1 is greater than B. That means you have a scenario like this. AB, this is A1, this is B1. B1 is greater than. Then what happens? This implies length of IK length of IK is greater than or equal to B1 minus B1, which is certainly greater than. Therefore, in that case, the inequality is valid. Okay. Then this result is true. That means you have this inequality. Now, suppose suppose B1 is not greater. That is the other possibility. Then that is B1 is contained in A, right? B1, there exists an interval in the collection IK (1 to n), say A to B2, distinct from A1 B1, A1 B1, such that B1 is B2 and which implies the following. So this is the scenario. And then of course what you have is that length of K equal to 1 to n. L is greater than or equal to B1 minus A1 plus and that gives this as B2 minus 1 A1, and this is certainly greater than A1, and that is greater than A1. Therefore, the inequality holds good in this particular case also. Suppose it doesn't stop with 2. You need more intervals to cover it. In that case, what happens? So, if the process is continuing until it terminates, we obtain a subcollection of intervals of such that A1 is less than AK plus 1 BK, n minus 1, and since the selection process has terminated, we have Bn. See, what is happening is this. This is A, this is B. We are working on this. Now you see, you have got A1, B1. Now what you have is A2, B2. It may not cover the whole thing. Then you choose an A3 inside A2, B2 such that B3. Suppose all the 3 do not cover. So eventually you should have A, N, Bn. So that the union of these intervals should cover this whole thing. Okay. So through finite number of steps you get a cover taken in this way, and then from this it is clear what follows. Now from this, it is quite clear that is greater than or equal to Vk, and this is of course equal to Bn minus An plus A1, and this you can rewrite as minus A, and this of course is greater than Bn minus A1, which is greater than. Therefore, we get this inequality that this is greater than B minus A, and now from the definition of M star of now you see, let us do this. Hence, the two inequalities taken together gives so that completes the proof when the interval is a bounded closed interval. Okay. Now what we do is, for any bounded interval, let us prove it now for any bounded interval, not necessarily. Now we prove it for then there exists two closed intervals such that See, the situation is this. Suppose this is your AB. A and B may be included or may not be. If it is both A and B are included, then you are talking about a close, the case that we have already considered. Suppose A is not included or B is not included or both A and B are not included. Then what you can do is you can find a closed interval. This is J1 and there is a closed interval J2. This is your I. So I is squeezed between J1 and J2 such that what is that you ask for? The length of I is minus epsilon is less than length of J2. J1 and the length of J2 is less than length of I plus epsilon. Now this is quite easily done because once you know these A and B, you can adjust the epsilon such that this particular requirement is satisfied. That's not the big. Can explicitly write down what this J1 and J2 is. See, for instance, J1 you can write as what is that you are writing it? This is A minus epsilon by 3 A plus epsilon by 3 minus J2 you write as A minus epsilon by 3 to B plus therefore this inequality will then satisfy. Okay. This is the choice that you this is one choice that you can do. Choose anything. Therefore what you have is this length of I minus epsilon is length of J1 and length of J1, you know, we have already proved this result that M star of a closed bounded interval is its length. Therefore this is nothing but M star of J1. Okay, and that's equal to that is less than or equal to M star of I, whatever it is, and that is less than or equal to M star of J2, that is less than or equal to, or that's equal to length of J2, which is less than length of I plus epsilon. So using this inequality, what does it follow? Start from here, this. So it follows that since this is true for every epsilon positive, we have Therefore, we have now proved this result for any bounded interval. Now, all that remains to be verified is what happens if the I is unbounded. So, we look at the case. Now, we take up the case. I is unbounded. That means it is an interval of the type minus infinity to plus infinity, or a to plus infinity, or minus infinity to b, something like that. Since I is unbounded interval, for every natural number n, there exists n j contained in I such that equal to, which implies m star of I greater than or equal to, because j is contained in I, and this is nothing but equal to length of j, which is equal to j. And this is true for every. Therefore, you see that m star of I is greater than or equal to n for every. Okay. And m star of I is, if it is an unbounded interval, m star of I is equal to length of I. Okay, so that's it. Right? Say, incidentally, in the three cases where you choose this is this. See, suppose the interval is infinity or something like a infinity. Then what do? You take the interval a plus n. Okay. Now, what is the length of this interval? The length of this interval is n. Okay, and that's also the m star of this. So, m star of this interval is certainly less than or equal to m star of infinity. Right? Therefore, we get this result. Similarly, if it is from minus infinity to plus infinity, you can choose the interval 1 to say, or 0 to n as j. If it is from minus infinity to b, then you can choose from b minus n to b as the interval j. and in all those cases this inequality is valid. Therefore, in all these cases we found that you choose any interval, whether it is bounded or unbounded, open, closed, or one side open and the other side closed, or you always get the m star, that is the outer measure, equal to the length of the measure. That is one of the major requirements that we need for the outer measure. So that eventually when you work with measure, after we introduce measure, you will see that we are assured that the usual concept of measure that we have introduced is essentially an extension of the concept of length for intervals. Okay, right. Now I think I'll stop this at this stage, and it remains to prove some more things, namely that the two more properties that we want to prove are m star of that is, it is translation invariant, and this property, namely for an m star of E2 and that is, it is subadditive, and again you can, from this we can show that it is also finitely subadditive. So that's the outer measure that you define for subsets of the real line. Now, one advantage is that it is defined for all subsets. Okay, we have relaxed equality here to subadditivity, and later you see that you will not, I mean, you would have to restrict the class of sets such that you can have additivity here. Okay, so with this remarks, let me conclude. Thank you very much.